What's yellow and red and coppery and peachy and green, other than every page in my daughter's coloring book? That's right, sunstone. Oregon sunstone, to be specific. The evocatively named sunstone really fits the bill, with coppery inclusions and wonderful eventurescence combining to flash a little sun in the palm of your hand. This seemingly innocent gemstone holds a secret, a dark secret that has haunted the dreams of those who dare search for the answer. Well, not really, I just wanted to say that. It's a gemstone you can dig out of basalt in southern Oregon. What else do you want? Actually, it's no joke that we haven't figured out all the mysteries of Oregon sunstone.
I'm not convinced that it is indeed a pyroxene phase, mineralogical compositional that causes the green.
We'll come back to that later. Before we get into the sunstones themselves, we should make sure everyone knows what I'm talking about, because outside of the Pacific Northwest, these unique stones aren't particularly widely known.
What the jewelers were putting in stones, whether it be topaz or rubies or emeralds, and those were the more famous ones. So when it comes down to some of the other stuff, garnets, we all think of a garnet as a star garnet, often, or zircons or opals. Opals are really unique. But when it comes to sunstone, they just never heard of it. Particularly the ones that are coming out of Oregon. There's no other places in the earth that are have those out there. And look, the red and stuff. So educating people is the key.
Maybe that isn't surprising, as they only occur in two small regions in the high desert of Oregon, where the population basically consists of the mine owners and whoever's digging sunstones that day.
From a geochemical perspective only, the two main locations where sunstones are found, you could make an argument that they are very geochemically similar, which is why I think originally we sort of thought that, they're all contained in Columbia River basalt lava flows, and the two lava flows that host them sort of at the northern mine, the Ponderosa mine, and then down at the sort of southern mines, the plush claims down there, about 100 miles as the crow flies, that they were the same composition. So sure, maybe we could correlate them as sort of the same eruptive event. However, the age data or the geochronological data tells us that actually they are very different and these lava flows are not the same. And the northern mine, the lava flows are about 16 million, which corresponds to Columbia River basalt age, mid-Miocene. But down at the plush claims, those lava flows are significantly younger at about 9 million. And so even though around the plush area, spatially, you're really close to Steens Mountain, so there has been an assumption that the plush area sunstones are contained in Steens basalt lava, also part of the Columbia River basalt. Their age tells us a different story. And so with 7 million years between these eruptions, there's no way they were part of the same sort of eruptive event. And the thing that I would say that they were sort of more associated with at 9 million is the high lava plains, which there's active research sort of arguing whether or not the high lava plains trend is associated with the Columbia River basalts and the Yellowstone hotspot. But yeah, with 7 million years apart, from an age perspective, they are not part of the same lava flows. When we date things, we can get an age for the ground mass, so basically the basalt that hosts the sunstone, and we can get an age for the sunstone. And in a perfect world, those ages match, or they're within error of one another. One thing that's complicated with Oregon sunstones and the basalts that host them is that more often than not, they don't agree, which gets to be problematic. And I think that also can sort of provide evidence that maybe there are two different processes at play. That is why we get these sort of like discrepant ages between the basalt and the sunstone. And so when I say that the northern mine is like 16 million and the southern mines are 9 million, I feel confident saying that because we've done, I would say, at least 15 ages in both locations. And the ground mass, so the basalt, those are the ones we have a little bit more of. And those are relatively consistent for both locations, where the sunstone ages are kind of wacky. We take our sample and there's a nuclear reactor on campus, and we bombard it with electrons to turn one of the isotope of potassium, the parent, into a different isotope of argon, and then we can measure the two isotopes of argon relative to one another with a much higher analytical precision than you can measure an isotope of potassium to an isotope of argon. So yeah, we've done argon-argon laser ablation. We've done oxygen isotopes, so like stable oxygen, down at the University of Oregon. With a number of these, when we get we call it an age spectra, so there's different ways we can calculate an age, it doesn't really make sense. Some people have argued like, oh, well that means, right, that sure, the basalts erupted and they have their ages, and then the ages that you're getting for the sunstones represent some sort of resetting. Maybe it's from hydrothermal, right, it gets hot, and it's resetting the plage ages. And the temperature at which that happens is roughly the same for the basalt and the plage. So if you were to reset the plage, in theory, you would also reset the basalt. And I cannot think of a way in which you could systematically reset all the plages at both locations and not the basalt. Not saying it's impossible, but right, you always want to start with your observations and your descriptions, like your field observations, and then your data, right, your results, and then move into the interpretational side of what that means. And the ages make that very complicated because they don't make sense together. The idea is that maybe when you have a magmatic eruptive activity occurring in the Columbia River basalts, around 16.5 million, that is sort of when sunstones are forming. And I'm going to say sunstones are forming in terms of a crystal perspective. So take out the copper for right now. The crystals are forming. When the northern mine, the Ponderosa mine, when that is in place, so when that erupts, it's associated with magmatism from the CRBs. You can get these sort of interesting sill-like or kind of pancake features in the crust. The Ponderosa mine, that material is erupting, and there's some stuff just like left in the crust. Fast forward 7 million years, and the high lava plains volcanism is occurring, and new batches of basaltic magma, are coming up from the mantle and basically punching holes through these sort of like pancakes of plage and then bringing them to the surface. That is the working hypothesis because that would sort of make sense of the ages that we're seeing. There are other sort of geodynamic problems that would introduce, like how are these things getting sort of retained over such a decent spatial area? Why don't we see almost like xenoliths or like really big crystal clots? Because if this is how these things were formed, you would think in the younger mines at the plush claims, you would kind of expect to see almost like clots of crystals instead of discrete ones. And more or less, we don't really see that. So I understand that this working hypothesis would then present a suite of other questions. It still has nothing to do with copper, right? This is just thinking of like how you could get basaltic lavas with gem quality plagioclase that are also spatially, geochemically, almost indistinguishable.
Now, this is where I would normally cut to a pan of sunstone mines interspersed with a conversation with one of the sunstone miners. However, I didn't make it to the mines before the digging season was over, so we aren't going to get that footage here, since I don't want to wait 6 months for the start of next year's mining season before releasing this documentary. And the only reason I couldn't make the trip is because I just didn't have the time and money to spend on it. If you like these kind of projects, please consider joining my Patreon to help make even better videos in the future, and you also get perks like early access videos and behind-the-scenes stuff.
Quite an experience. It's beautiful country down there.
Which mine did you go to again?
I went to the Spectrum mine, And Denise is the one that is her name. Very, very nice, very pleasant. She does the managing of the customers coming in and wanting to do that. They've mapped out where their next digs are going to be. It was real nice, real convenient when they got things all set up and ready. They came in with a backhoe and with a big scoop on the front, and they had which I guess would be a yard. They dumped in a hopper and it came down. One guy sat on a stool where it came down and kind of spread them out as it came through on the belt. And just before that point, water is flowing onto the belt, and so it makes it easier to spot the color from the gravel. So I was the first one, my friend was second, and then they had another woman there at the end, and she was picking off whatever we missed and saved it. And at the end, they gave it all to us, gave it all to me, because that was what we missed.
So, Eastern Oregon. Much like with Washington, when people think of Oregon, they think of the west side of the Cascades, Portland, the Goonies. But a lot of the Beaver State lies east of the mountains. There's the Wallowa and Blue Mountains in the northeast, and the central Ochakos, but overall much of it is high desert, with broad expanses of basalt and cactus and sagebrush. Bend is 2/3 of a mile high, Plush is 85% of the way there at 4,500 feet, and it's in this sparsely populated region that we find Oregon sunstones. Plush, in particular, is the main area of collecting. Lesser known is an area around Burns, Oregon, with a similar exposure of sunstone-bearing basalt. That area isn't as well publicized because the mines there aren't open to public digging. It's the area near Plush that hosts BLM public access lands where one can go and scour the desert floor for gemstones, and there's an assortment of private mines nearby that have fee digs during warmer months.
They have a public area down there, and in the public area, you can walk, I'm told you need to walk in about a mile from the public area in that land that's set aside for the public to get to an area that hasn't been dug. You gotta put in more work to get in there. You can't drive into it, you gotta walk into it, park in the public area, and then you walk in, and that's where you're likely to find it. And the sunstone can be at the surface, or it can be 1 foot down, or 3 foot down, or 10 foot down. It's where that strata layer is that crusted over, and underneath that is where the sunstone are. And I'm also told it's better to do it early in the morning when there's a little dew on the ground, because then the sunstone, they say it just sparkles.
Sunstones are a gem variety of feldspar with enough clarity and quality to be worked into cabochons and faceted stones. Faceting them is how I became interested in the subject, but everyone has their own discovery period.
For part of my PhD, I was thinking about sort of correlation of lava flows within the Columbia River flood basalts. And so you could say that I started researching sunstones in 2016, but how it sort of manifested itself was not with the intention of studying sunstones, it was with the intention of looking at the lava flows that they were in.
The Fasteners Guild would be contacted by people who had gone over to Eastern Oregon and collected sunstones, and now they want somebody to cut them. And so they would contact the guild, and one of the people that receives those inquiries would forward over to a few of us and say, are you interested in cutting? And so I thought, okay, there's a little extra way to make a little extra money to help me advance my business, and I did. A couple at the time, they came with 8 or 10 of them, and I think I cut in the end 14 of them for them. And one of them cut it in a triangular one. When I first looked at it, all I saw in there was red. But when I started to polish that, green showed up. It wasn't visible anywhere until I reached that point. And it was such a stunning green. It captured me so much that I wanted to cut more.
I said sunstones are a feldspar. Feldspars are a mineral group of aluminosilicates with proportions of potassium, sodium, and calcium differentiating subgroups like oligoclase from albite or whatnot. Sunstones are compositionally labradorite, and if that name sounds familiar, it's probably because you know it from this form, the opaque mineral with an iridescent oil slick type sheen. That sheen, or labradorescence, is actually kind of like Schiller, just like in sunstones and moonstones, which are also labradorite by the way. While we're on the subject, we should talk about other sunstones and some sunstone imposters that are out there. There are a couple of other locations with sunstones, like Norway, although for the most part they're cab grade rather than facet grade, meaning they have too many inclusions or are too opaque to facet a sparkly gemstone. There's also the Viking sunstone, aka Iceland spar, which you may have heard about as the way Vikings would navigate in cloudy weather. This is by all accounts not a feldspar at all and is optical calcite. There's cool history and science behind it though, so go check out this video by Skaldun for more on Iceland spar.
There are other locations that have been proposed around the world that can get a bit contentious based on maybe who you talk to, but there is one place that there may sunstones that are comparable. So labradorite, right, plagioclase feldspar has been found with copper, and it's in Ethiopia. And this other potential location in Ethiopia is the second youngest flood basalt in the world. It's about 35 million. I find just kind of interesting that potentially the only two places that we're seeing sunstones are within the spatial extent of flood basalts, and they're the two youngest in the world. And so maybe these things are actually recording some sort of unique petrogenetic process, so some sort of unique, right, magmatic process that's happening within the material that's sequestered in the crust during these eruptions, but their preservation potential isn't very high, and they're pretty localized features. And so that's an area of interest for me, and I think part of the motivation behind why I'm still interested in studying these.
There are probably a few other sunstones out there because, after all, lots of people look to the sun for inspiration, but there have also been purposeful imposters. Specifically, in the early 2000s, a bunch of red andesine, which is a type of feldspar, came on the market. But the thing is, it quickly became apparent that something was kind of off about it. Nobody could verify where the mine came from, and for a long time only finished pieces were available, with no rough or even offcuts of rough. In 2008, someone finally gave in to inquiries and brought some of that rough to market, and it very quickly was confirmed that the stuff had been heat treated due to diffusion of copper into colorless andesine. There's a great article on the Jewel Cutter about this if you want more detail. So forget about that, let's get back to real sunstones, from Oregon. The most common variety is relatively pale yellow, sometimes called champagne-colored. These are the sort of baseline variety that aren't considered very valuable, although they still look great when faceted. The real money is in colored sunstones, which can be red, green, or both, and modifying that appearance, any of these varieties can have copper schiller. Grading these colors takes an experienced eye, as market prices range from $10 to several $100s per carat, depending on the richness of color.
And I'll spend time with a stone under a light rotating around and trying to see where do I want the table, or what do I want the table to look like. Get that faced up and then mount it onto a dop stick and start going at it.
But, of course, beauty and value is in the eye of the beholder.
I had another mother, father, daughter. They were from the Corbett area. They had gone again to the mine or the belt, and they picked out some, and they came, and all three of them were different. He wanted a ring, she wanted a necklace, and the daughter wanted one, but they're all three different, and they were just so tickled to death in the end of how the gems turned out. And I wasn't charging a lot of money for that, but the gratitude, I mean the reward out of that was how they felt about the stones. They went as a family, gathered them, they had them cut, and they all had something made into a piece of jewelry that they'll always have, and they'll always remember each other in that event. So the faceting of stone is not just cut it, but it has meaning of life to people, and that's neat bringing that to somebody.
One interesting aspect about colored sunstones is that the zones are in the middle of the crystal, surrounded by this champagne. So where do these colors come from? Just like with schiller, it's all from copper, I think.
You know, sometimes when they're cut, you get red and sort of like peaches, but then you do get sort of these really nice, almost like green tones. Now, the way this one is cut, like there is sort of a streak of green almost in the center, but sometimes you get almost like looks like watermelon. And I've heard these referred to as watermelon, sometimes also bicolor, where red is in the center and then it has a nice little green rim. There's been a lot of proposed ideas about this. Some people have said it's just like different sort of oxidation states of copper, right? Because if you've ever seen it like a copper pipe, right? Sometimes it has like that green color, but there was no evidence for that sort of on more of like a microscopic scale. Also, how would you change it in such a really close proximity? We also don't see the platelets that you see in the red in the green. So if it was indeed just like a different oxidation state of copper, you would at least expect to see in some material, right? The platelets would still be there, they'd just be a different color, and we don't see that. More recently, about 5-ish years ago, there was a paper that identified the green zones to indicate the presence of protoenstatite, which is a kind of bizarre clinopyroxene. On a phase diagram, this is really high temperature, relatively low pressure. The temperature range and the pressure range, it's really hard to come up with a geologic scenario where you could get that and it could erupt and not revert to some other more stable state. Still pyroxene, but not this like very specific protoenstatite. One of the reasons I start to question maybe whether it's the presence of protoenstatite is because, in addition to us not really seeing this as something that's actually found in the natural world, there are certain sunstones, namely, I'm just going to pick this one because we've noticed this, is that this is just, right, you could call this champagne maybe, but effectively it's colorless. And we started lopping off little corners of it when we did argon and for laser ablation. Like, we've used this one. And what I've noticed is that as we cut off chunks, the optics of it look a little weird, and now I can see a green zone through this. And I start to wonder how much of the green is compositional versus potentially structural, something going on. Some of them, this was supposed to be just schiller, and then once you break it, you start to see these different colors that weren't evident before you smashed it. I'm not convinced that it is indeed a pyroxene phase.
Or even mineralogical.
Mineralogical compositional that causes the green. I like the idea, and the paper that saw this, they did have some evidence. I can't remember the method that they used, but it was very much sort of like on the microscopic scale. Nano inclusions, like once you get to the nano size, if you scaled up, they don't work the same once you get to that really, really, really small scale. And I don't know enough about sort of nanoparticles to come up with like an alternative thing of why I don't think it's protoenstatite, but to me I feel like I haven't seen evidence that would suggest that it's compositional or mineralogical in nature. Because I can see a green zone right now, and they move. So like if we broke this, where that green area would move. And so that tells me that there's something more like optically that's happening. Also because I teach petrography at OSU, I've taught petrography at OSU the last 2 years, and petrography optical mineralogy, so we use a petrographic microscope and we look at thin sections, and there is a optical property, right? So you have your physical properties of minerals, and you can also have optical properties. Some physical properties can be optical properties, so something like twinning or cleavage planes, so those can be something physically you observe about a mineral that you can also see in thin section under the petrographic scope. But one optical property that typically isn't a physical property because it's very hard to see it on a large scale just with your naked eye, is something we call pleochroism. And basically at different crystallographic orientations, you'll see different colors in a mineral. To me, when I look at the red and the green and the fact that when you rotate it, I'm seeing those colors change, either from what looks to be colorless to green, and also change in intensity. So also like how blue or green it is. This reminds me of pleochroism. And in that sense, it's not driven by a compositional difference or mineralogical difference. It's more a crystal structure difference.
I've cut them trying to orient the copper to show its best in a stone. I kind of like rectangular cuts better than round cuts because the rectangular cuts can, you get more room to work with something. You got a bigger, I will say, a palette for no other term, but a bigger palette to work with, so you can do something that. When it comes to sunstone, my feeling is the simpler the cut, the better. I don't think you need to, because particularly with a sunstone with copper in it, you're not going to get the light bouncing out of the pavilion like you would with a sapphire or a corundum or a spinel or something like that, where it's one solid color, because the light doesn't really come back out through there. It doesn't pass through the copper, it just reflects. So I want to let that show. I try to orient that with the table and just let it be that. If it has colors or red, it's always nice to have one solid color in there or a slightly variation of that. But I also like having a band of color in there with no color on either side or one side. So it really shows what the stone is all about. They're all beautiful. Every one is different. Even if it has a faint color, if you can find a color. Some of that stuff just comes from the experience of either cutting them or being around other cutters to tell you what they'll, do this, don't do that, or this is how this works, or that's how that works. And you just have to determine for yourself what you believe, what's right, because there's a lot of people that tell you what they believe is right, but it's really not what the truth is.
You look at these things and they're, right, they're beautiful. And the fact that you can just go out into Eastern Oregon and find them is pretty wild. And so I think it's kind of the sexy stories ooh, copper, this is cool, it's red, we're finding these beautiful red crystals just out in the high desert. It's cool, right? And so you get sort of, not blindsided by it, but it's very attractive. Yeah, yeah, sure, exactly. It gets exciting and you want to just kind of dive into that. But then it just took me a while to realize I should take a step back and think about this. If the goal is to think about this as a geologic, magmatic problem, how are the crystals forming? Make sense of that first and then layer in the copper. It's definitely, I'm not saying you can't think about them together because there is some value in that, but I think by focusing on the copper right off the bat, it almost worked as too much of a distraction from maybe some of the more telling observations that we could have made.
And there are definitely open questions about sunstones, made extra difficult because there's a lot of overlapping processes occurring, and it can be tough to keep them straight even when just talking about them like this. The sunstones are found in different basalt units, and the sunstones may have crystallized in the crust before being entrained in the basalts. So was the copper in the stones from when they crystallized, or were they diffused in after eruption? And did those color zones form during crystal formation or sometime later?
Whether or not sunstones formed in situ or not, I think has been a hot topic of debate, but I'll specify that the crystals themselves are definitely magmatic. Sunstones, the mineral is, it's a feldspar, it's a plagioclase feldspar, and then very specifically it's labradorite. And feldspars cannot form at sort of hydrothermal temperatures. Also, I've heard people say, oh, the crystals formed in the vugs or the void spaces in the basalt, but the temperature at which feldspar forms. That can't happen. So the crystals themselves definitely formed magmatically, but the formation of sunstones in terms of sort of when the copper was introduced is still, I would say, up for debate. We have some bits of data that suggest that the copper was introduced to the feldspar at magmatic temperatures, and then other bits of data that say the copper was introduced more at like surface conditions and probably from hydrothermal processes. I think also because the basalt that hosts sunstones is typically, if anyone's seen it, right, it's kind of friable. It's pretty oxidized. You know, sometimes you can get fresher material, but for the most part, when you find these really big crystals, they're in kind of this, it's consolidated, but it's pretty weathered. So that would suggest that maybe there, you know, this has been exposed to more hydrothermal processes, and that's what introduced the copper. So the crystals definitely formed magmatically, but the color in the copper is one thing that we're still trying to understand more about. And because certain bits of data conflict with one another, it's making unraveling that story particularly spicy. My heart thinks it's magmatic, or my gut. Maybe I could say my gut thinks it's magmatic. However, there are people who are experts in copper. John Dillis, who is an emeritus professor here at Oregon State, we've had some lengthy discussions about this. And from his perspective, we've talked about this being hydrothermal. I think the other layer of confusion becomes under what valence, sort of what charge, the copper was introduced to the material. So if we want to make it a little more complicated, while I do think the copper was partitioned into the feldspar at magmatic temperatures, I do not think it partitioned in as metallic copper or copper zero. It was probably a different charge valence, and then there was some exsolution process that then sort of turned that into what we think of when we see a sunstone and we see, right, these little nano inclusions of metallic copper. So maybe it's actually a combination of two processes, right? So the crystals form magmatically, maybe the copper is somehow introduced to the crystal also magmatically, but it doesn't exsolve and sort of form these little copper nano inclusions that we see until sort of closer to the surface. Under different, and maybe hydrothermal conditions or processes are part of that. And the more data we see and the more sort of complicated things get, I'm starting to think that almost we're both right, or both kind of camps of thought, right? That there is, like, yes, the crystal formed magmatically, but then when it comes to copper, maybe there's actually two things going on. Part of the reason I also say that is sunstones are bizarrely unzoned in major and trace elements. And by that, I mean, if you imagined yourself right in the center of a sunstone and you did sort of a geochemical analysis, and then you slowly walked to the edge of a sunstone, taking different kind of geochemical samples, it's surprisingly like uniform or homogeneous from the core of a sunstone to the rim. There are certain elemental differences, like copper. Obviously, you can imagine there's higher abundance or concentration of copper in the center of a sunstone where it's red, and less on the rim where it's relatively clear. But there are also other elements that are that correlate with copper, and also sort of inversely correlation, like lithium, interestingly, has an inverse correlation to copper within sunstones, and that's some active research that we did here in Adam Kent's lab, who runs the laser ablation ICP-MS lab. And actually that was a lot of fun because we had some undergrads helping out with that. So in terms of sample prep and analysis, and there were 3 undergrads that actually presented on some of that at a local GSA, Geological Society of America, sectional meeting, which was pretty cool. But the fact that they're unzoned, even if you take the fact that we see copper out of it, like the fact that we see red in the center, if we take that out and we just consider the fact that these things are really unzoned and basically gemstone quality, that's interesting too. And so how you do that even without copper is a bit, I don't want to say bizarre, but you're not finding gemstone quality plagioclase like all over the world. So there's a part of me that wonders, the presence of copper, is that sort of distracting us from other interesting aspects of sunstones that may be formed from the same or a slightly different process.
One thing I was curious about was the observation that the sunstones are relatively unzoned, apart from, like, copper. I figured if they were altered, there would be something that leached out or diffused into the crystal to throw something off between the core and the rim of larger crystals. And sometimes in a closed system, you see changes from core to rim just due to components being used up.
For the most part, you don't get a core and a rim. You kind of pick a sunstone, and then we smash it so they get like little pieces, and then you end up loading those in a tray, and then there's a laser that hits those. However, because a lot of these sunstones are so big, what we did for some of them is, and you could probably imagine maybe doing something with one like this. We actually smashed it, and in an intentional way, so that we could separate what was the core that had like a high density of color and like that, or even had like the copper platelets, from the like bits along the rim that were totally colorless. And then we'd analyze those as two separate samples. And I'm glad you asked this, because one thing that we have noticed that is a bit interesting, although I will say that we don't probably have enough samples to say definitively if this is definitely representative, but we have noticed a difference in the oxygen isotope value between the center of a crystal that has a high density of color and the rim of the same crystal that is totally colorless. And it is a difference in those values that is not possible to do from sort of standard magmatic changes alone. Especially interesting because, right, we don't see significant major trace element changes, which, if the difference in oxygen isotope values from those two places, the core and the rim, were from magmatic processes, you would expect to see that in other evidence of that. And there was one crystal that I first did this for in like 2019, and then I recently, me and a student did it just this spring. And what was really cool is we got the exact same value from the core of this crystal as I did in 2019. So I feel really good that the value that we have is like very accurate. What was interesting is that the rim gave us, from 2019 to more recent analyses, gave us different, but in both cases, they're significantly different from the core. So while we don't get the spatial resolution that we would with laser ablation, if you have a big enough crystal and done sort of carefully, you can at least separate high densities of color in the center or the core of the crystal from the rim that maybe doesn't have anything. And I do think there's something significant there. What it is, I don't entirely know, but one great thing about oxygen is that the lab, one of the best labs in the country, if not the world, is right an hour away at the University of Oregon, and it's relatively cheap compared to other analytical things where, you're talking like $1,000 a sample or something. Oxygen is like, under $50 a sample. So we could absolutely expand that data set, but before doing so, wanting to make sure that, like, now that we've found this is interesting, like we've done it twice and we do see a difference, that would probably be the place that I would focus, because the undergrad that worked on this, Scott, did determine that there wasn't a significant difference in oxygen isotope values between locations or between colors, loosely. But looking at one sunstone from a high density of color to colorless, we were seeing. And that is sort of more interesting because you're looking at one crystal, which really should have the same value spatially. So that would be an area that I'd want to look into further. But to do that, you need a large crystal that has high density of color in the center. And those are more expensive. So convincing people to give you, I mean, if something's fractured, it's easier to do, right? Because people can't cut it. But sometimes with this, it's hard. It was really hard to smash a beautiful sunstone so that we could, right, analyze it in different ways. But, you know, taking something like this and smashing it with a sledgehammer, I have a video. I didn't do it. One of the students did it, sort of, and it was fun. We got a little slow-mo video of it, but it's kind of sad. So trying, if we wanted to see how representative this difference is across more sunstones, we would have to just get more material. And I think it's not outlandish, but it's a little bit harder to do, especially because you're just destroying them. Which is kind of sad. But this one would work.